Okay, so now we're going to talk about apparent weight. And this is an important idea to understand as we continue to move through our study of forces. So an object, if an object is subject to gravity and is not in free fall, then there must be a reaction force to oppose gravity. And we call that the apparent weight. So if you're in an elevator, the weight never changes. The force of gravity never changes. And so, this is, again, your actual weight. And so, you can feel lighter or heavier depending on, how you're accelerating in the elevator. And we're going to explore that here. So let's explore that here. Let's say we have a person standing on a bathroom scale, and we wanted to find the person's apparent weight. And so what we would do is we could draw the free body diagram of the person, and that person standing on the scale, the force would be the force of gravity, and then the apparent weight is the normal force here. And what we're going to look at is the different situations here. So this is positive y, negative y down here. And when the person accelerates upward to positive 2 meters per second squared, what would the apparent weight be? So we don't know what this would be because if we're just standing there, sure, the normal force would be the same as force of gravity, the apparent weight would be the same. But in this case, we look at some force of y equals a negative y. We have the positive normal force plus the negative force of gravity. And we do have an acceleration, which would be the mass 85 times positive 2 meters per second squared. And the force of gravity is just mg, so what we can figure out is the apparent weight, what the normal force would be. So in this case, the normal force would be 1003, as we get that. Now when the elevator is moving at a constant velocity, what do we know is true to constant velocity? Change in velocity is zero. Velocity final minus velocity initial, right? So if that's zero, the acceleration is zero. So what would happen here would be the normal force would be equal to the force of gravity. We bring that to the other side. Some of the forces, right? The acceleration is zero. So this would be the apparent weight, which is actually equal to the real weight, force of gravity on the person. Now, what would happen here if the elevator begins to slow as it moves to the top floor? So here would be picture here, and then the acceleration would actually be downward, negative 2 meters per second squared. So when we set up the sum of the forces here, and we want to find the normal force, the force of gravity, we can figure out what the apparent weight is. And if you can think about what that feels like if you're coming up to the top floor and you're slowing down to stop, that would feel like. So why don't you go ahead and set up the sum of the forces, and sum of the forces equal to MA, and you can try this one. Okay, so we've got our force of gravity. We know the acceleration is negative, and that's going to be a really important thing to recognize here. If it gets to slow, the motion is going upwards, so therefore, if it's slowing, the acceleration is downwards. And it turns out to be the apparent weight's only 663, much less than we saw before. That's because the acceleration is downward, and you feel a little bit weightless. Not completely weightless, but less than it would be before. Okay, so on this one, go ahead and set up the free body diagram and see if you can determine the values here for A, B, and C. And as you do that, you can determine what the apparent weight is for each scenario. So for this fish, we've got the force of the scale upwards, the force of gravity downwards. And so see if you can determine what the spring force is, and essentially what that would be the apparent weight for each of these scenarios. And then you can start the video when you're ready. Okay, so for the first one, the tension force, you could have had the spring force as well, like I put on the last slide. We have the some of the forces in the X. There's no forces, so we don't have to worry about that there. And then in the Y, we have the tension force up, force of gravity down, and we get a tension force of 49 newtons. Now, moving upward and slowing, so that would mean that it's going upwards, but because it's slowing, the acceleration would be downwards, therefore negative 3.2 meters per second squared. We would have a force of 33 newtons as our tension. And then finally, moving downwards and speeding up. So we're moving downwards, but we're speeding up, so the acceleration is downwards because we're speeding up. So we would get a also apparent weight of 33 newtons. So the common mistake here is to not recognize what the acceleration is and then put in an incorrect value. Okay, so let's try another sample problem here that we have where a bag is being accelerated upward at a rate of 2 meters per second squared. And we want to find the minimum tension strength so that the rope will not break. So go ahead and draw the free body diagram, set up the sum of the forces with the equals mass times acceleration. See if you can figure out what the minimum tension would have to be for this to work. Okay, so you should have set up force of tension going up, force of gravity going down. Set up the sum of the force in the X. There's no forces, so no acceleration in the X and the Y. We have the positive force of tension plus the negative force of gravity equals ma. And it is positive acceleration. It's being accelerated upwards. So the force of tension that would feel would be 259.6. So the minimum, absolute minimum, would be that value. But in reality, we probably want something a little bit more than that.